our next speaker is actually Yucheng. And his talk, I find it really interesting. Because normally when we talk about actually scale, we think about actually scaling into many, many machines. But what Yucheng is going to share is that how to scale a problem down to a single machine so that you can page rank the entire Twitter using a single machine. So please welcome Yucheng.
Thank you. Good. OK. So this talk is a little different from previous talks. In fact, it's quite different. Is this a controller? Okay. So far, most of the talks are talking about query processing, kind of as looking at services and that sort of thing. This one, we're going to look at kind of computation, just straight computation for machine learning. OK, so how many of you have heard of GraphLab? OK, good. It was founded in mid-2013, or it was called GraphLab by Carlos Gestrin, my advisor at the time. And it's, because graphs are important and everywhere. Everyone wants to be able to do something with graphs, but graphs are hard, right? But machine learning is much more than graphs, right? So we end up expanding. We do a large amount of all kinds of machine learning, deep learning, recommender systems, and so on. And so the name kind of does not work quite well anymore. And so we renamed to Dato in January this year. Right, and the objective of Dato is to be able to take machine learning all the way, starting from data exploration, machine learning, all the way to production. Okay, but unlike the name change, today we are actually going to talk about graphs. Okay, so call this guy graphs the Dato way. So what is the Dato way? So many systems, at least even kind of looking at computation, right? Well, I did a lot of this as well, kind of like large distributed computation. We begin by assuming unbounded resources, and we optimize for runtime because that's what makes papers. You go faster and faster and faster, try to go as fast as you can, right? But what happens then is that what was built does not work very well on one machine. You end up with limiting scalability on a single machine or a small cluster, even as the single machine gets increasingly powerful now with GPUs and so on. So what we have done instead is to flip it around. Let's assume there are bounded resources on built for a single machine. Let's build the problem, define the problem in a way so that we only have bounded resources, and we optimize instead for scalability on a single machine. And then, as we extend it to go distributed, you end up with something that scales excellently, scales amazingly, and requires fewer machines to solve the same problem in the same runtime. So the core issues with scaling graphs revolve around very, very classical data structure problems. Data representation. How am I going to represent the graph? How am I going to do computation? And how am I going to distribute the execution? So let's look at kind of a really basic graph representation question. We have this little graph here among Alice, Bob, and Charlie. Now, the simple representation is just a table of vertices. Now, note we're going to have attributed vertices. So this is just a table. We have an ID column, that's the vertex name, and maybe address, zip code, and so on and so forth. And similarly, we have an edge table. So each edge is one row in this table. We define edges, and maybe we have attributes on edges as well. So this, once again, is just a table. So each one of these are tables. So one of the first foundational data structures, they are really useful here if we want to scale out, is to be able to have external memory or disk or SSD-backed table representations. Right, and this is what we have. We call it an SFrame. So the SFrame is exposed via a Python API, and what it is scaled out of core table representation. It's a columnar representation internally with lazy evaluation, compression, all the interesting stuff. We are constantly making improvements on it. What's cute about it is that in addition to regular data types, we also have relatively weak schema types like arbitrary lists, arbitrary dictionaries, arbitrary recursive ones, which then we have operators that let you manipulate those, unpack those in columns, stack them, or manipulate them in different ways. Or take a string and interpret them as convert them to a dictionary, and that's basically a JSON parse. Right, so we can do a really quick demo of how SFrames work. Okay, so this is a Python API. And the package, while the name has changed to Dato, the package is still called GraphLab. You can just import it. We're going to load an SFrame directly off an SSD. Loads are instantaneous because the backend is really a columnar database-like representation. So we just point to it, right? And let's look at how big this thing is. 950 columns and 930 billion rows, a million rows. So there's 1 billion rows and about 1,000 columns, so about 1 trillion cells, right? So column names, yeah. So what this was is a biology data set. It's a kind of a mutation data set, right? We're going to look at kind of viability of mutations. We took it and we artificially replicated it to make a really, really large table. Sorry. Okay. Scroll. Okay. We can look at the contents of the SFrame. This will pull the first, it'll take about 4 seconds, and we'll pull the first 100 rows. As with all demos, things have a tendency to fail. This kind of depends on network because I'm pulling it. This is actually running on a remote machine. Okay, so this is all the columns, the first 10 rows of each column. We can query an arbitrary row. There's a degree of random access that's capable. Right, what we can also do is that, collapse. What we can also do is that we have some visualization capabilities. We can show the entire table. Okay, let's give a few seconds. Once again, this depends a lot on network availability. Okay, so this is actually going to show all the columns and all the rows in the table. All 1 billion rows. You can scroll to an arbitrary location, and we just fetch the corresponding rows appropriately, and we just display. So it really doesn't matter how big your original table is. But it does fetch a bunch of rows across the network, so we are bounded by bandwidth here. Okay, so we can do all kinds of columnar operations. Internally, it's a columnar database, so we can very quickly, for instance, sum a single column, right? So there's 1 billion rows. It takes about a second to sum it. We can pull out individual columns and do arbitrary manipulations on it. We have all the vectorized operators, so you can add and add columns, subtract columns, insert new columns easily. Okay, let's go back to the slides. Okay, so that's the SFrame. And that gives us a nice disk-backed table representation. But the objective for the graph, what's the design objective for the graph here? We don't want to support, so firstly, it's immutable. We are going to look for immutable graph representation, append only, so you can add vertices and add edges after. We have arbitrary vertex and edge attributes, and this is one key difference of our graph data structure. We are optimized for bulk access, not fine-grained queries. So unlike a lot of graph databases, we are not going to do things like get neighborhood of vertex 5 efficiently. But we aim to be able to answer questions like get neighborhood of all 5 million vertices relatively efficiently. Okay, so the basic layout we went after is a simple partition layout for the vertices. So we take we just arbitrary hash partition the vertices into 4 tables, into 4 SFrames. So each one of these is just one SFrame columnar represented. So, and then for the edges, we partition the edges into a squared number of partitions. So here we have 4 vertex tables. So here we have 16 4x4 edge tables. So the layout is based upon the adjacency matrix. So each shard here is essentially one table. So what happens now is that the layout is, so edge partition 2, 4. Okay, essentially contains all edges connecting vertices in partition 2, 2 vertices in partition 4. Okay, and then the inverse query is also fast. So if we want to look for all edges connected to vertices in partition 2, we just need to look at this set of edge tables. Okay, so now, so this is kind of the basic layout. We have vertex tables, we have edge tables, and partition into 4 and 16 shards respectively. But this is kind of wasteful. There's all these strings here, right? We do not want strings. Strings are very wasteful, very difficult to encode. So, but it's really common. String IDs are really common. Usernames, email addresses, hashes, and so on. So a simple trick is with each vertex table really has implicit numbering, which is this is the row number, right? 0, 1, 2, and so on. And we can just translate these using the implicit numbering. And this increases compression because we have columnar compression. We get something really, really compressible. Most integers are small. And also the partitioning helps a lot here. So if you think about it, say we have 4 billion vertices, that's a minimum of 32 bits per vertex, right? And maybe 64 bits per edge, ignoring compression. But because we partition into 4 shards, it means that each shard maybe only has, say, 1 billion vertices per partition. And so within each shard, we can save 2 bits for each vertex ID. Okay, so so this is kind of the basic principles of this representation. With a columnar data representation, we can also do things like, while your graph is much bigger, with a lot of attributes, the fields unrequired for computation are not accessed and can just be there. We don't need to touch them at all. So because with columnar databases, it's fast to set along columns. We can also add new fields to the same table cheaply. And compression lets us kind of reduce the number of bits required per edge. And with the columnar type of compression mechanisms, in all the integer compression tricks, we can bring that down, bring the representation down quite significantly. So we ran this, tested this on the common crawl graph. This is the largest publicly available web graph we can find. 3.5 billion vertices, 128 billion edges. So represented naively, it's about 2 terabytes. That's 8 bytes per ID. We represent about 200 gigabytes or a compression factor of 10 to 1, 12.5 bits per edge. So generally speaking, you can do better with much better, with more sophisticated methods, but this gives us kind of a nice balance of capabilities. We can do relatively good lookups, as well as being able to look through the tables, manipulate tables, the edge list efficiently. So this is the idea of kind of this compression is really simple. If we look at the basic storage hierarchy, which everyone's familiar with, disks give you about 200 megabytes per second, SSD 500 megabytes per second. And if we can get a 10x compression, and if we only do sequential accesses, this brings each disk and SSD up to bandwidths which are commensurate with memory. And we run this on one machine. So GraphLab create, this is PageRank on the Twitter graph. One machine, we can run this at speeds comparable to a few other distributed systems, GraphX and Giraffe. And for connected components on one machine, we are much faster. Once again, this is on the Twitter graph, which I've been thinking is just about 1 billion edges. Now, on the common crawl graph, about 128 billion edges, we use one machine, one EC2 machine, one SSD. We can run PageRank on this. 9 minutes per iteration, connect components about 1 hour. So there really isn't any other general purpose system out there capable of this. You can do this yourself. Right now, this software is publicly available. So that is representation. Let's go on to computation. So I've worked on graph computation for a very long time, and it's a problem we've thought about for a while. We began with kind of our first GraphLab paper, which was in 2010, which was how the name of the company originally came about. And they defined kind of this think like a vertex computation idea, where you write these vertex programs, which manipulate state around the neighborhood of a vertex. Right? And then we take it distributed in Power Graph with new ideas for how do we decompose this computation further for distributed to work well for power law graphs, and how to cut vertices for how to partition the graph well for distributed computation. So we're going to use PageRank as an example here because it's simple and it's easy to explain the abstractions in the context of it. Right? And the PageRank is not very complicated. The rank of a particular user is essentially a weighted sum of my neighbor's PageRank. Okay, and we update everything in parallel until convergence. That's it. So we have a new computation abstraction we call triple apply. And while previous models being vertex-centric, we have gradually taken the resolution lower and lower. So how do we pare it down to an absolute minimum? And so now we consider graph computation kind of an edge-centric model. You see the graph one edge at a time, but you can access the data on both ends of the vertex. And this is executed in loop until convergence. So PageRank can be very easily written in this formulation. And now we can take this and we can parallelize it further just by sweeping over through all the edges in a nice ordering. Okay, and we do this by having a mixed in-core, out-of-core computation. We have the edge list in our sharded format on disk, and we have the vertex page ranks in memory. Right? And if we sweep over the edges in kind of a Hilbert curve ordering, we get really good cache access patterns in memory as well. So there are ways to do this with out-of-core vertices carefully with some additional techniques, which I will not, we're not going to here. So next is the distributed graph problem. So as a system, we're able to achieve serious performance, really good performance with really careful I/O design on bounded memory systems. But then essentially what we are doing here is kind of what happens if we take some of these constraints away. We no longer have, we have really big machines, right? So if we have designed really carefully to be I/O optimized, then once we have a distributed systems, we have parallel disks. And parallel disks are essentially embarrassing parallel. So any part of the code which just does straight disk access, we just get straight linear speeds up within those sections of the code. And you have any excess memory on the system, that's the I/O cache. We can either let the operating system handle it, or we can handle it ourselves, and that gives us even greater speed ups, right? So, but there's one lingering question when it comes to distributing graphs. There's a question of graph partitioning. How do we cut the graph over the network? And the objective of graph partitioning is to minimize communication, reduce communication costs. However, unlike many other graph systems here, which kind of like you place vertices and you let edges span across machines, what we're gonna do here are vertex cuts. Essentially, we're going to place edges on machines, and we let vertices span machines. This can be shown to be kind of provably better for power law graphs or natural graphs. They are very common. We talk about that a lot in the earlier power graph paper. So, however, graph partitioning, the objective communication minimization, but you kind of have this issue, which is how long it takes to compute a partition versus what's the quality of the partition. You can spend a long time to find a really, really good partition. You can hit it with things like Mattis and so on, which will find you a really, really nice partition. But then for the time spent doing the partition, you might as well do your actual computation, right? So there's this kind of balance here. So since really large natural graphs, which are very common, are very difficult to partition anyway, so here's the question. How good a partition quality can we get while doing almost no work at all? The first thing that comes to mind is random partition, just hash, right? So we just take the graph, and then everyone gets a random subset of the edges, right? So in this case, one thing is kind of balanced. So in this case, for instance, vertex Y spans 3 machines, vertex Z spans 2 machines, and so on. But this is probably also the worst partition can construct, right? So can we do better? So once again, we have this edge representation. We're going to cut it into 4 machines. How do we partition this? Very simple. Each machine takes, just takes a little square of the set of edge partitions. And no vertex is on more than 2 square root p minus 1 number of partitions. This can be shown to be much better than the random cut. But then the question comes in. What happens if it's not so easy to divide? What happens if I have 3 machines now? So here's the trick. So let's take the Hilbert curve ordering of the shards, and we're going to cut the Hilbert curve ordering. And so each machine takes a mostly mostly whole partitions, and then some partial tables. So this essentially lets us we do not actually need to do complex reading across the network. We can just do full file copies or whole block copies across the network. For the vast majority, we only need to decode a small set of partitions which are cut across machines. So these are slides from a couple of years ago, which are for Power Graph, which when Power Graph is scalable, that time was the largest publicly available web graph. 6.6 billion edges, 64 HPC nodes, about 2,048 hyper-threaded cores, 7 seconds per iteration, 1 billion edges per second. We have new results. So this is a common core graph. Once again, 128 billion edges. This is a speed-up curve we have. But what's the runtime there on 16 machines? 16 machines, C3-8X instances, 512 virtual cores, 60 seconds per iteration, or about 2 billion edges per second. This is rather hot off the press. It's pretty much unoptimized still, so there's still a number of improvements that we can go. So essentially, we have decreased the number of machines required by a factor of 8. The amount of resources required by a factor of 8 while doubling throughput. So we are by a factor of 4 while doubling throughput. So it's an order of magnitude more efficient, and with some optimizations, this can go much further. So the philosophy we take on scaling is essentially the same as our approach to implementing machine learning at Dato. So we have built a lot of things, linear models, trees, recommended algorithms. We have deep learning as well, clustering, and so on. And everything is kind of built along the same philosophy. So for instance, we can do matrix factorization on 20 billion user item ratings on a single machine, single commodity machine. And so that's true for kind of everything we do. We can scale every algorithm on a single machine to things which are much, much larger than what you can fit in memory normally. And we are also working on distributed stuff. We have early implementations of a few of the distributed machine learning algorithms. So it's not just about speed or scaling. It's easy to throw machines at problems until you scale, or easy to throw machines at problems until you run fast enough to beat all other benchmarks on this problem. But it's kind of being able to do more with what you already have. And lastly, I will end with a shameless plug for our conference, which is in July in San Francisco next month. Thank you. Questions? Or there's going to be lunch, and you can ask me questions. No? Hi.
Thank you for a great presentation. So with these graph performance numbers, it's very hard to know how really state-of-the-art this work is relative to all the activity in graph computation. Is it a standard benchmark for example, page ranking or something where you can rate yourself relative to others? It's hard to know how much better. Are you pedal to the metal? Is this the best you can do? What is the speed of light for this particular kind of processing?
Yeah, so it is hard to get good comparison numbers. But the best place to understand this kind of comparison numbers is really kind of papers. And you kind of take the published papers. Sometimes we have open source code, and we can take those and run them, right? But some systems, for instance, Pregel which was Giraffe was inspired by Pregel. Pregel at Google, that's kind of close, and that's supposed to be quite good, but there's no way to get any kind of numbers on those. Right now, on the distributed side, the big ones are Giraffe and GraphX, and right now, essentially, we're way faster than them on a single machine while they are on a cluster, as we had some benchmarks earlier for the Twitter graph. There are a number of research stuff as well.
You are faster on the single machine because?
We are faster on single machine. Exact reasons are complicated. It's a question of abstraction, architecture, compression, and so on, right? But I had some benchmark slides earlier, where essentially we are faster on a single machine than they are on 16 or more. Yeah, the details will be technical. We can take that. We can take that offline. It's a mixture of kind of abstraction, implementation, and architecture. Yes.
So in your demo, you are using some custom version of IPython or a notebook, or can I just treat it as a library and then use a normal IPython notebook?
I'm not using a custom IPython notebook. This is a regular IPython notebook. Yeah, they rebranded to Jupyter, but you still install IPython notebook. But the project is now called Jupyter. So yes, we behave as just a library.
You use the space filling curve to do the graph partition, and I just wonder if the graph is not dense, it's sparse. You still can achieve a good partition strategy there, comparing to Mattis or other the options there.
Yes, so the graph is generally sparse. We do a space filling curve on the edge shards, which are dense. So we have like 8 by 8 shards in the No. Anyway, in the examples was the vertices were partitioned in 4 shards, edges were partitioned in 16 shards, and we do a space filling partition on that 4 by 4 set, not on the actual graph itself. That would be very expensive.